Okay, so this is example program, Unit C3, page 7. Once again, this is siphon example program, but with added information to the siphon itself. Let's take a look. Water at 60 degrees F. Oh, wait a minute, temperature is given. I don't know why, but the program gives you temperature information. Do we need that? I'm not sure. We can find out. So anyways, water at 60 degrees F is siphoned from a, again, large tank. It says so, large tank. 15 feet depth. It's probably a small size aquarium tank. 15 feet deep. It's a huge tank, isn't it? It's probably Shamu at San Diego. Okay? So this is a siphon using a constant diameter hose. Okay? Let's determine the maximum height of the hill, h. Here, maximum height, h, over which the water can be siphoned without cavitation occurring. The end of the siphon is 5 feet below the bottom of the tank. Oh, okay. So this is a huge, long hose. Goes up and down, 5 feet below the tank bottom. Okay. So this is, practically speaking, something real happening at probably San Diego SeaWorld. You know, you change the water from the huge tank, you use siphon. Okay. And then atmospheric pressure is 14.7 psi. Apparently this is the sea level, but do we need this information? Why this information is given? Let's find out. Okay. All right. So once again, before we take a look at this problem, let's just go back one page and let's review cavitation. Cavitation sometimes happens when it usually water becomes gas vapor. It is a change of phase. That's called cavitation. Cavitation can happen without change of temperature. Major factor of that cavitation is a change of pressure. So if there is a mechanism inside of your flow field to lower the pressure, at that lowest point of pressure, if that pressure hits the vapor pressure of a given temperature, actually cavitation starts to happen. Okay, so this is an example of cavitation within, this is called Venturi meter. Venturi meter is a flow rate measurement device, so you're going to attach this segment into the pipe flow. What it does is you're going to reduce the cross-section of the flow, accelerate the flow, creating the pressure difference between 2 points, and measure that pressure difference to determine the flow rate Q. That's the device, flow rate measurement device. But if you reduce the cross-section too much, you accelerate this flow too much, you lower the pressure too much. That happens to be this lower pressure. It's the lowest point. This pressure becomes vapor pressure for a given temperature. You begin to have a cavitation here. Cavitation means that you turn the liquid water into gas vapor of H2O. This is one such example. At the tip of the propeller here, because it's spinning really fast, velocity right here is really fast. If the velocity is high value, pressure goes down, Bernoulli's equation. If the pressure goes up, velocity goes down. If the velocity goes up, pressure goes down. Bernoulli's equation says so. So as a result, you can see the formation of bubbles. Those are not air bubbles. These are the gas vapor of water. It's cavitation. Okay? So now you're seeing that right here, cavitation is happening. Liquid water is no longer liquid, it's a gas vapor. And there's no temperature change involved. It's just pressure change. So let's go back to the problem here. So this program basically asks you if you put this hose really high. If it's too high, what happens? Right here, the pressure goes down. This is the minimum pressure point throughout the process of siphon. If this H is really high, pressure goes down and down and down and down and more. If the pressure is too low, right here, cavitation starts to happen. The condition of that is to hit the pressure here becomes equal to the vapor pressure of a given temperature of the water, which is 60 degrees F. That's why this information is necessary. Okay? This temperature determines what is the vapor pressure of this water. Vapor pressure is a function of temperature. So for a given different temperature, vapor pressure will be a different value. So this is a standard value, so water of a room temperature. So let's begin with picking up the value. Looking at your property table. So this is the water at 60 degrees F. If that's the case, what is the vapor pressure PV? You need to look up the table of property, standard property table. It is going to give you 2.26 times 10 to minus 1 psi. This is the vapor pressure if the water is 60 degrees F. Okay? If the water comes with different temperature, this body will be different body. So let's be careful. Okay. So the condition of that is right here, 0.2. This is the lowest pressure throughout this siphon. If the pressure here becomes this pressure, whoa, we are going to develop cavitation. Okay? So that actually determines maximum height of H right here without having cavitation. Okay, that's the purpose of this problem here. So this is 15 feet deep water, which is really deep. Plus the hose goes down 5 feet more. Okay. Then the problem says this is 0.1 right here on the surface of the water. This is a zero gauge pressure, free surface. Velocity V1 is approximately 0. Why is that? It's large tank. Okay. What else? This is the location 3, where the water comes out. Now obviously we know this is a free jet, so the pressure here is local atmospheric, which is 0 gauge. This is a free jet. So I'm going to define a streamline. This is a location 1, of course, slowly picking up the speed and sucked into the hose, and then once it's sucked into the hose, it's going to flow like that. This is a streamline. Okay. So I can apply Bernoulli's equation between any location along the same streamline. So what do I want to do? First of all, let's apply Bernoulli's equation between location 1 and 3 to find out free jet velocity. That's what we did in the previous example. So let's do that. Bernoulli's. Between 1 to 3. This is going to give you equation P1 plus 1/2 rho. V1 squared plus gamma Z1 is equal to P3 plus 1/2 rho V3 squared plus gamma Z3. Right? P1 is 0 gauge, it's a free surface. P3 is also 0 gauge, it's a free jet. Keep in mind, this is gauge, okay? So I'm using gauge pressure in this equation. Let's be careful about that. Okay. B1 is approximately 0. This is a large tank. Okay. Oh, where do we measure Z? Let's measure Z from tank bottom. So I'm going to measure Z from here. If I do that, Z1 becomes 15 feet, right? Z3 becomes minus 5 feet. Minus 5 feet. Okay? Well, obviously, you can set any location of this datum or difference line anywhere. So if you measure Z from here, it's going to make Z3 is equal to 0, and then Z1 is 18. It's going to be the same thing, right? Same exact equation you get. So it doesn't matter where you measure Z from. Okay. So this now becomes, this is a 0 and 0, this is gamma Z1 is equal to 0, 1/2 rho B3 square minus, it's okay, plus gamma Z3. So let's solve for B3 here. B3 is square root of 2 times gamma over rho Z1 minus Z3. Gamma over rho is G. So this is a 2 times G. Z1 minus Z3. Which is square root of 2 times G. G is 32.2, let's plug in. Let's assume standard suitable gravity. Multiply by 15 feet minus 5 feet. So you ended up adding minus of minus. Double negative. So you ended up having 15 plus 5. Total 20 feet. So this gives you B3 is equal to 35.9 feet per second. Okay? Then I kind of stop and think, wait a minute. I think I have a feeling that I've seen this equation also. Yes, let's take a look at page 2 again. So page 2, free-jet equation. What is the velocity right here? Velocity right here is square root 2 times g times this h times this h. Both added together, it's going to be the velocity right here, v5, which is larger velocity than v2. Exactly, yeah. So that's what this velocity here is. Velocity here is square root 2g times this depth times that depth, 20 feet, is going to be this value. Okay? So again, this is a free jet velocity. Yep, something we know already. Okay? And then another thing is continuity applies within the host. Continuity. Within the constrained flow, which is host of this flow, you can say Q is constant, flow rate everywhere is constant value. And then this is constant cross-section area host. Okay? So that means velocity everywhere is constant. So once you find B3, the velocity here is also the same, and velocity anywhere within the host is the same. B3 equal to B2, which is 35.9 feet per second. Okay? So continuity tells you that. So now, I'm interested in finding this h, maximum value h. This maximum value corresponds to if the pressure here becomes this value, that's where the cavitation begins. So that's the lowest, absolutely lowest possible value you can have without cavitation. So suppose if pressure here becomes this value, what is the H? That is what I want to find out. So let's apply Bernoulli's once again. Let's apply Bernoulli between 0.2 and somewhere that we know lots of information. That's probably 2 and 1. You can possibly solve the same thing between 2 and 3. If you apply Bernoulli between 2 and 3, you can also solve the problem. So I'm going to choose 2 and 1. The reason here is because one of them is 0. So 0 is easy one to handle because I can just cancel out. So Bernoulli's equation applied between 1 and 2. Like I said, you can do the same thing between 2 and 3 and you can solve the problem. Okay? P1 plus 1 half rho B1 squared plus gamma Z1 is equal to P2 plus 1 half rho B2 squared plus gamma Z2. Okay, let's take a look at each term of this equation. P1. Oh, P1 is the gauge. I'm going to underline gauge, emphasizing, hey, this is, I'm talking about 0, but this is 0 gauge. B1, approximately 0. Large tank. Z1, measured from here, 15 feet. P2. P2, okay, well, the condition of P2 is, suppose if P2 becomes this value, that's where the cavitation begins. Plug in this value here. So this P2, if it becomes vapor pressure of a given temperature of water, that's where the cavitation begins. This actually determines the maximum value of H, okay? So, B2, we know that. This is B2. Oh, Z2. Z2 is H. That's what we want to know. So, question is PB. So we do know PB is this value. And then this value is PSI, absolute pressure. This is a gauge pressure. You cannot mix up gauge pressure and absolute pressure within the same equation. You can't do that. So you have to either convert this gauge into absolute and use absolute pressure, or you can convert absolute into gauge and use the gauge pressure. Either one's fine. But which one is easier? I think converting absolute to gauge is easier because one of them is 0. Okay? So keep in mind, vapor pressure is given 2.26 times 10 to minus 1 pounds per inch square. This is gauge, this is absolute pressure. I have to convert it to gauge. How? Well, I need some information. What kind of information do we need? Well, we need information of local atmosphere. So, okay, so what is PATM then? I need that while it's given. So that's why atmospheric pressure is 14.7 psi. This statement is necessary. Without this, you cannot finish up this problem. That's why this statement is added. Okay? So how do we convert this? Let's subtract 14.7. This is going to get you gauge pressure. Gauge pressure, this is supposed to be big negative value, right? Yes, of course. Vapor pressure is big vacuum pressure. Okay? So this is going to get you a minus 14.47 pounds per inch squared. This is gauge. Let's convert it to PSF. Conclusion. Vapor pressure in gauge in pounds per square foot is minus 2083.68 pound per feet square. This is gauge. Important, I want to use gauge here and also gauge here. Both gauge pressure. You can't mix up gauge and absolute. So this is a PSFG. Okay. So let's finish up. So this Bernoulli's equation now becomes so this becomes 0 and 0. This is 15 feet gamma times Z1. Z1's being 15 feet, right hand side. P2 being vapor pressure. 1/2 rho B2 squared. We know B2. Then gamma Z2. Okay. So this really means that 62.4 pounds per cubic foot, that's the gamma of water. Z1 is 15 feet. Is equal to P2 is minus 2083.68 pounds per feet square. Vapor pressure plus 1/2 density of water, 1.94 slugs cubic foot. Velocity V2 is 35.9 feet per second, this thing square, plus gamma again, 62.4 pounds per cubic foot, multiplied by Z2, which is H. So this equation involving one unknown H. Then you can solve for H. So if you pick up your calculator, solve this one for H. H is equal to 28.36 feet. But wait a minute. This is not the maximum. Maximum elevation is slightly lower than that. So this is actually, if you go for this much height, cavitation happens. So in order to avoid the cavitation, this elevation must be smaller than this value. Okay? So that's your answer. So this is, again, siphon. Okay? Siphon, which involves with condition of cavitation. And then also, this is application of Bernoulli's equation and continuity. So let me just remind you once again, the difference between continuity equation and Bernoulli's equation. Bernoulli's equation can be applied any location along a given streamline. So before you apply continuity, you have to determine streamline to begin with. That's very important. Continuity equation can only be applied if the flow is constrained. In this case, just within the flow of hose. Right here, you cannot apply continuity. For example, point 1, this is the surface of a large tank. Large tank means cross-section area becomes infinity. That's why velocity can be taken as close to 0. This is the violation of continuity, by the way. So I'm purposely violating continuity right here. So you cannot apply continuity anywhere between point 1 to inlet of this hose. Okay, that's the location where non-constrained flow, you can never use continuity. Continuity can be applied within the hose. Continuity tells you velocity is uniform throughout the hose. Okay, those are the important things that you need to remember. Okay, that's it.